Welcome to the series of e-learning modules on conditional probability and independent events. In this module, we are going to cover the conditional probability of dependent and independent events, and also the application of multiplication theorem of probability in real life. By the end of this session, you will be able to know the meaning of conditional probability of independent events, multiplication theorem of probability, application of conditional probability and multiplication theorem. Conditional probability is the probability of an event in the subpopulation or in the reduced sample space. It is the probability of an event given that the other event has already taken place. For instance, if we consider any two events A and B, then the conditional probability of event B given A is the probability of happening of the event B when the event A has already happened. Probability of B divided by A is not defined if probability of A is equal to 0, and A by B is not defined if probability of B is equal to 0, because we cannot divide a number by 0. For a fixed B with probability B greater than 0, probability of A by B is a probability function. This result can be proved as follows. To prove this, first we should show that it satisfies three axioms of probability. The first axiom being probability of the event is greater than or equal to 0. The second axiom, probability of S or the sample space is equal to 1. The third axiom is if for any set A n is any infinite or finite sequence of disjoint events, then probability of union of AI is same as the summation of probabilities of AI. Now, we apply these axioms to the conditional probability. Since P A intersection B is greater than or equal to 0 and probability of B is greater than or equal to 0, as both are probabilities which are greater than or equal to 0 and less than 1, also the numerator is smaller than the denominator. Considering the left hand side and replacing A by S in the second condition mentioned above, we get probability of S by B is equal to probability of S intersection B divided by probability of B is equal to probability of B divided by probability of B is equal to 1. Since S is a sample space and B is a subset, their intersection will be set B. If set of A n is any finite or infinite sequence of disjoint events, then probability of union of A n given by B is equal to the probability of union of A n intersection B divided by probability of B. Since the denominator is independent of n, we can take it inside the summation. Here we proved that probability of A by B satisfies all the axioms of the probability. Therefore, probability of A by B is a probability function. Independent events. Two events are said to be independent if occurrence or non-occurrence of one does not depend on the occurrence or non-occurrence of the other. Conditional probability of independent events. If the two events are independent, then conditional probability and unconditional probabilities become equal. Therefore, probability of A by B is equal to probability of A, and probability of B by A is equal to probability of B. That is, outcome of one event does not influence the other event. Result 1. If the events A and B are such that probability of A is not equal to 0 and probability of B is not equal to 0, and A is independent of B, then B is independent of A. This result is proved as follows. Given that A is independent of B, therefore probability of A by B is equal to probability of A, implies probability of A by B is equal to probability of A intersection B divided by probability of B, implies that probability of A intersection B is equal to probability of A into probability of B. Probability of AB is equal to probability of A into probability of B, implies probability of B intersection A divided by probability of A is equal to probability of B. Since probability of AB is equal to probability of BA and probability of A is not equal to 0, this implies probability of B by A is equal to probability of B, which by definition of independent events means that B is independent of A. Result 2. If A and B are independent events, then A and B complement are independent. A complement and B are independent. A complement and B complement are independent, where A complement is complementary event of A and B complement is the complementary event of B. The above result can be proved as follows. If A and B are two independent events, then the probability of simultaneous occurrence of A and B is given by probability of A given B is equal to probability of A, and probability of B given A is equal to probability B. Also, probability of A intersection B is equal to probability of A into probability of B, which is equal to probability of A given B into probability B, which is equal to probability of A into probability of B given A. As B and B complement are complementary events, probability of B plus probability of B complement is equal to 1. Consider probability of B given A plus probability of B complement given A is equal to 1. Then probability of B plus probability of B complement given A is equal to 1. Substituting probability of B given A is equal to probability B implies probability of B complement given A is equal to 1 minus probability of B is equal to probability of B complement. Hence, A and B complement are independent. Second condition, as A and A complement are complementary events, probability of A plus probability of A complement is equal to 1. Consider probability of A given B plus probability of A complement given B is equal to 1. Probability of A plus probability of A complement given B is equal to 1. Substituting, probability of A given B is equal to probability of A implies probability of A complement given B is equal to 1 minus probability of A, which is equal to probability of A complement. Hence, A complement and B are independent. From 1 we have A and B complement are independent. Therefore, probability of A given B complement is equal to probability A, and probability of B complement given A is equal to probability of B complement. Therefore, probability of A given B complement plus probability of A complement given B complement is equal to 1. Probability of A plus probability of A complement given B complement is equal to 1. Substituting, probability of A given B complement is equal to probability of A implies that probability of A complement given B complement is equal to 1 minus probability of A, which is equal to probability of A complement. Hence, A complement and B complement are independent. Multiplication theorem of probability. From the definition of conditional probability, we can define multiplication theorem of probability, which is the probability of happening of two or more events simultaneously, as probability of A intersection B is equal to probability of A into probability of B given A. If the events are independent, the statement reduces to probability of A intersection B is equal to probability of A into probability of B. Result: in the slide, we have given the multiplication theorem for two events. Suppose if there are n events, namely A1, A2 up till An, then the probability of happening of n events simultaneously is given by probability of A1 intersection A2 intersection so on so forth up till intersection of An, which is equal to probability of A1 into probability of A2 given A1 into probability of A3 given A1 intersection A2 and so on up till probability of An given A1 intersection A2 intersection up till intersection of An minus 1. This result can be proved using mathematical induction. If there are two events, A1 and A2, then probability of A1 intersection A2 is equal to probability of A1 into probability of A2 given A1. The probability of event A1 and the probability of event A2, given that the event A1 is already happened. If there are three events, A1, A2 and A3, then probability of A1 intersection A2 intersection A3 is equal to probability of A1 into probability of A2 given A1 into probability of A3 given A1 intersection A2. The probability of event A1, the probability of event A2, given that the event A1 has already happened, and the probability of event A3, given that the events A1 and A2 have already happened. Similarly, if there are k events, then probability of A1 intersection A2 intersection so on up till intersection of AK is equal to probability of A1 multiplied by probability of A2 given A1 into probability of A3 given A1 intersection A2, so on up till probability of AK given A1 intersection A2 intersection up till intersection of AK minus 1. The probability of event A1, the probability of event A2 given that event A1 has already happened, and the probability of event A3 given that the events A1 and A2 have already happened, and proceeding like this, the last term will be the probability of the event AK given that the events A1, A2 up till AK minus 1 have already happened. Therefore, in general, if there are n events, then probability of A1 intersection A2 intersection up till the nth item is equal to probability of A1 into probability of A2 given A1 into probability of A3 given A1 intersection A2 up till probability of AN given A1 intersection A2 intersection etc. up till intersection of AN minus 1. Illustration 1. Here is a problem of drawing a card from a pack of cards which is a heart, given that it belongs to the red suit. In a pack of cards, there are 52 cards and 26 of red suit and 26 of black suit. Further, there are 13 cards which belong to hearts. Let us define the events. A. Card drawn is red. B. Card drawn is a heart. By definition of probability, probability of A is equal to 26 by 52 and probability of B is equal to 13 by 52. Further, happening of both the events, which is probability of A intersection B, is equal to 13 divided by 52. Cards belonging to red suit and heart. Therefore, by definition of conditional probability, the probability of drawing a heart, given that it is red, is given by probability of B given A is equal to probability of A intersection B divided by probability of A, which is equal to 13 by 52 divided by 26 by 52, which is equal to 1 by 2 or half. Illustration 2. Here is another example of throwing two dice, where some of the numbers obtained on the two dice are noted, and we need to find the probability that the numbers obtained on both the dice are even, given that the sum is 4. When we throw two dice, the numbers we can have on both the dice are 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, and similarly 2 1, 2 2 up till 2 6, 3 1, 3 2, so on up till 3 6, 4 1, 4 2, 4 3 up till 4 6, and 5 1 till 5 6, and 6 1 till 6 6. Therefore, we have 36 equally likely, mutually exclusive, and exhaustive outcomes while throwing two dice. We can define the events as follows. A. The sum of numbers is 4, and we have three combinations of numbers which give us the sum 4. They are 1 3, 2 2, and 3 1. Hence, probability of A is equal to 3 by 36. Let us consider B. The numbers on both the dice are even. We have only one combination, the combination 2, 2, where the sum is 4 and both the numbers are even. Hence, probability of A intersection B is equal to 1 by 36. Therefore, by the definition of conditional probability, the probability of getting even numbers on both the dice given the sum is 4 is given by probability of B given A is equal to probability of A intersection B divided by probability of A, which is equal to 1 by 36 divided by 3 by 36, which is equal to 1 by 3. Let us take another illustration. Two dice, one green and the other red, are thrown. Let A be the event that the sum of the points on the faces shown is odd, and B be the event that at least one number 1 appears. Find the probability of the events. A given B, B given A complement given B complement, and B complement given A complement. From illustration 2, we have the sample space of 36 equally likely, mutually exclusive, and exhaustive outcomes while throwing two dice, maybe red and green as in this case. Event A is given to be the sum of the points on the faces shown is odd. There are 18 combinations where we get the sum odd. Hence, probability of A is equal to 18 by 36, which is equal to 1 by 2. And probability of A complement is equal to 1 minus probability of A, which is 1 minus 1 by 2, which is equal to 1 by 2. Event B is an event of at least one number is 1. That is 1 1, 1 2, 1 3, 1 4, 1 5, 1 6. We also have 2 1, 3 1, 4 1, 5 1 and 6 1. Observe that there are 11 combinations of numbers where we get at least one or two, 1 in the combination. Hence, probability of B is equal to 11 by 36, and probability of B complement is 1 minus 11 by 36, which is 25 by 36. Further, the event A intersection B has the following outcomes: 1 2, 1 4, 1 6, 2 1, 4 1 and 6 1. Observe that there are 6 combinations of numbers, the events both A and B. Hence, probability of A intersection B is equal to 6 by 36, which is equal to 1 by 6. A complement intersection B complement is given by using the relation A complement intersection B complement is equal to A union B complement. The event A union B has altogether 23 elements. Hence, probability of A union B is equal to 23 divided by 36. And the probability of A complement intersection B complement is equal to probability of A union B complement is equal to 1 minus probability of A union B, which is equal to 1 minus 23 by 36, which is equal to 13 by 36. Having probabilities of different events, we can find in the first case the probability of A given B, which is the probability of A intersection B divided by probability of B, which is 1 by 6 divided by 11 by 36, which is equal to 6 by 11. For the second case, the probability of B given A is equal to probability of A intersection B divided by probability of A, which is equal to 1 by 6 divided by 1 by 2, which is equal to 1 by 3. For the third case, we have the probability of A complement given B complement, which is equal to the probability of A complement intersection B complement divided by probability of B complement, which is equal to 13 by 36 divided by 25 by 36, which is equal to 13 by 25. In the fourth case, we have the probability of B complement given A complement, which is equal to the probability of A complement intersection B complement divided by the probability of A complement, which is equal to 13 divided by 36 divided by 1 by 2, which is equal to 13 divided by 18. Illustration 4. A bag contains 10 gold and 8 silver coins. Two successive drawings of 4 coins are made such that, first one, coins are replaced before the second trial. Second one, coins are not replaced before the second trial. Find the probability that the first drawing will give 4 gold and the second drawing will give 4 silver coins. Let us define the two events as follows. Event A, drawing of 4 gold coins. Event B, drawing of 4 silver coins. A bag contains 10 gold and 8 silver coins. Hence, together there are 18 coins. And first we draw 4 gold coins. Hence, the probability of drawing 4 gold coins will be given by probability of A, which is equal to 10C4 divided by 18C4, which is equal to 10 into 9 into 8 into 7 divided by 4 into 3 into 2 into 1 divided by 18 into 17 into 16 into 15 divided by 4 into 3 into 2 into 1, which is equal to 7 divided by 102. When the coins are replaced before the second trial, the events A and B become two independent events, and hence probability of A intersection B is probability of A into probability of B. The probability of selecting 4 silver coins are given by probability of B is equal to 8C4 divided by 18C4, which is equal to 8 into 7 into 6 into 5 divided by 4 into 3 into 2 into 1 divided by 18 into 17 into 16 into 15 divided by 4 into 3 into 2 into 1, which is equal to 7 divided by 306. Therefore, the probability that the first drawing will give 4 gold coins and the second draw will give 4 silver coins is given by probability of A intersection B is equal to 7 divided by 102 multiplied by 7 divided by 306 is equal to 49 divided by 31,212. When the coins are not replaced before the second trial, the event B will depend on the event A, and hence probability of A intersection B is equal to probability of A into probability of B given A. The probability of selecting 4 silver coins in the second draw is given by probability of B given A is 8C4 divided by 14C4, which is 8 into 7 into 6 into 5 divided by 4 into 3 into 2 into 1 divided by 14 into 13 into 12 into 11 divided by 4 into 3 into 2 into 1, which is 10 by 143. Therefore, the probability that the first drawing will give 4 gold coins and the second draw will give 4 silver coins is given by probability of A intersection B, which is equal to 7 by 102 into 10 by 143, which is equal to 70 by 14,586. Illustration 5. A fair coin is tossed thrice. What is the probability that all the three tosses result in heads? Here we are tossing a fair coin thrice. Since the coin has only two faces, head and tail, the probability of getting a head in a toss is 0.5. Hence, we can define three events A, B, and C as follows, since we have toss thrice. A, the first toss results in head. B, the second toss results in head. C, the third toss results in head. Probability of above events A, B, and C are same and equal to 0.5. Since A, B, and C are the results of three different tosses, they are independent. Therefore, the probability that the number of tosses result in head is given by probability of A intersection B intersection C, which is equal to 0.5 into 0.5 into 0.5, which is equal to 0.125. Illustration 6. The odds against manager X settling the wage dispute with the workers are 8:6, and odds in favor of manager Y settling the same dispute are 14:16. What is the chance that neither settles the dispute if they both try independently of each other? For this problem, let us define the events as follows. Event A, the manager X will settle the dispute. Event B, the manager Y will settle the dispute. Given that odds against manager X settling the dispute with the workers are 8/6, hence P A complement is equal to 8 divided by 8 plus 6, which is equal to 4/7. Odds against the complementary event, and hence probability of A is equal to 1 minus 4/7, which is equal to 3/7. The odds in favor of manager Y settling the same dispute is 14:16. Hence, probability of B is equal to 14 divided by 16, which is equal to 7/15. We want to know odds favor minus given event. Hence, probability of B complement is equal to 1 minus 7/15, which is equal to 8/15. Therefore, the required probability that neither settles the dispute, which is given by probability of A complement intersection B complement, is equal to probability of A complement multiplied by probability of B complement. Using the result when A and B are independent, then A complement and B complement are also independent, is equal to 4/7 multiplied by 8/15, which is equal to 32/105. Here's a summary of our learning in this session. Meaning of conditional probability. Independence of two events and their probability and some basic results. Multiplication theorem of probability and results. Application of conditional probability and multiplication theorem through different illustrations.